Hello everybody, and welcome back to my SB2 channel. So this lecture is all about the shapes of the molecules with respect to their polarity, both the polarity of the bonds and the polarity of the overall molecule. Okay, so we're going to be talking about all of that, and then we also have a practice at the end. As you remember in one of our previous lectures, we talked about the dipole moment, right, and the polarity of the bonds. So just a kind of reminder here, for a molecule consisting of more than two atoms, the dipole moment is going to be depending on both the polarities of the individual bonds and the overall molecular geometry. For each bond in our molecules, we need to consider the bond dipole, which is representing the dipole moment, and that is mainly because of the electronegativity of the two atoms that are making that bond. So we're going to be looking at the case of CO2, which is a very common molecule, carbon dioxide, where we have a linear shape for that in the next two slides in a lot more details. Okay. Okay, so for our CO bonds in our CO2, both of these bonds are going to be polar, and therefore we can use arrows, as you can see on this picture, to present their polarity. Now, since the CO bonds are identical, their bond dipoles are going to be equal in magnitude, but look at them. They are in the opposite directions, right? So now the question is what we can say about the overall dipole moments of this molecule. Okay, so it seems that we don't have any overall dipole moment. It seems that it's zero. So let's talk about why this is zero on the next page. Okay, so the bond dipoles and the dipole moments are going to be always our vector quantities, meaning that we need to consider both their magnitudes as well as their directions. The dipole moments of a polyatomic molecules is always the vector sum of all of its bond dipoles. Okay, so having said that, in your CO2, the two bonds that we have are polar, so I have two bond dipoles, right? Although they have the exact same magnitude, they are pointing in the opposite directions. So if you try to add them, right, they're going to give us zero because they are pointing in the opposite directions. And therefore, the bond dipoles cancel out each other, and the overall dipole moments of CO2 must be zero. Even though the individual bonds are polar, the molecule itself is nonpolar due to its symmetrical linear geometry. Okay, so be careful with both your bond polarity as well as your overall polarity, right, for our structures. Okay, cool. Now, there's another example for you on the next page. Now, let's consider water, a bent molecule where we have two polar bonds. Since the two OH bonds are identical, their bond dipoles are going to be exactly the same in magnitude. However, due to the bent geometry of the molecule, the bond dipoles do not directly oppose each other, and therefore they're not going to cancel out each other. As a result, water has a net dipole moment, and that has been measured experimentally, which is 1.85 dBi, making it a very polar molecule. The oxygen atom are going to carry out partial negative charge, and the hydrogen atoms are going to carry out a partial positive charge. Okay? And you can see their arrows and the bent geometry on our picture on the right side. Okay, so that means overall the molecules with polar bonds can be either polar or nonpolar, depending on their geometry and the distributions of the bonds. Generally speaking, molecules where we have the central atom symmetrically surrounded by identical atoms such as BF3 or CCl4 are going to be nonpolar because their bond dipoles are going to cancel out. So let's take a look at a couple of more examples. So yes, BF3, as we said, it is nonpolar. HCl, which is hydrochloric acid, this one is polar. CH3Cl, this is known as chloromethane. That's also polar. NH3 is ammonia, and that is also very polar, right? You've got a pair of electron on your nitrogen. And we also have CCl4, which is carbon tetrachloride, and that one is also nonpolar due to the cancellation of all these vectors in our tetrahedral geometry. Okay, excellent. Take a look at our practice on the next page. So here's the question. Predict whether these molecules are polar or nonpolar. So if you look at BrCl, I need to start by drawing the Lewis structure. And this one is kind of easy because I only have like two atoms. I just need to connect them, right? So that is a linear shape. However, I know that the electronegativity for chlorine is more than bromine. So I'm going to draw my dipole moment as something like this, right? Pointing toward chlorine. So this molecule must be polar, right? Okay, now take a look at the next one. SF6. Okay, so I've got 6 bonds on the Lewis structure for this molecule. 4 of them are on the same page, right? Or same plane. And then the other 2 are kind of perpendicular. If you remember from our previous lecture, this is all about your octahedral geometry, right? And they're going to all cancel out each other. That is going to give us a non-polar molecule, right? Due to the cancellation of all of these dipole moments for the bonds. Okay, thank you very much. If you like this video, go ahead and give it a thumbs up. If you have any comments, please let me know. There's going to be a lot coming up for you soon. Take care of yourself, and bye-bye for now.